Hello everyone, welcome to week 8 of group theory. Our theme this week is the concept of group actions, and in the first of this week's short lectures I'd like to try to explain what that concept is about by way of some examples, and then in the second installment we'll have a look at the more formal aspects of the definition. So really, group actions are a very important concept in applications of group theory to geometry and topology, and to lots of situations where you're interested not only in groups as abstract entities in their own right, but for where you visualize groups as acting on something else, as doing something to something else. We've already seen many examples of this phenomenon without necessarily emphasizing it from this viewpoint. And one obvious example is the case of groups of permutations. So we're going to go back to that example from last week in S14, but the comment for now is just that when you're talking about groups of permutations, you're talking about groups whose elements permute things. So with a group of permutations, your elements are permutations, they're functions from some set to itself, but what the elements of the group are doing is they're permuting things in some set. The set is not part of the group, but it's there in the background and it's a really important part of the setup. So in the language of group actions, we would say that the group is acting on that set. And what that means is that every element of the group is behaving as a permutation of the set. Okay, so that's kind of explicit in the case of groups of permutations, but it happens in other situations as well. So for example, in the case of general linear groups, the elements of our group are matrices, and it's sort of conventional and typical to think of matrices as kind of objects that have their own arithmetic. You can do calculations with them, you can calculate their inverses, you can multiply them together and so on. But you can also think of matrices as linear transformations. And in that setup, if you take a group of invertible matrices, like the general linear group of 2 by 2 invertible matrices over the real numbers, let's say, then each matrix is acting as a linear transformation of two-dimensional Euclidean space. So you can think of the matrices, if you want to, as moving elements around in two-dimensional space. So there you would say again that the group GL2R is acting on the two-dimensional Euclidean space. Its elements move around points in two-dimensional Euclidean space. So that's the viewpoint of group actions, that you have a group and that its elements are moving things around somewhere that's outside of the group, but where there's an interaction between the group elements themselves and some other set. So just to make it a little bit more explicit with some examples that are familiar to us before we pin down all the definitions. So here's the example that we had last week. It's a permutation in S14. Here it is. So it's a permutation that takes 1 to 11, 2 to 9, and so on. It's a function from the set consisting of the integers 1 through 14 to itself that sends every element to a different image. And here's its disjoint cycle representation. So just to recall, what that's saying is that the permutation pi takes 1 to 11, takes 11 to 3, takes 3 to 8, and so on, eventually takes 6 back to 1. But separately from that, pi takes 7 to 12, 12 to 13, 13 to 10, and 10 back to 7. And here I've included also the fixed point 5. So 5 is taken by pi to 5. Okay, so as we've seen before, pi has 3 cycles, including the fixed point. They have lengths 1, 4, and 9. And this is a description of pi that shows that pi permutes all 14 elements, but it permutes the 9 that appear in this cycle amongst themselves. Separately from that, it permutes 7, 12, 13, and 10 amongst themselves, and it permutes 5, well, amongst itself by descending 5 to 5. So it breaks up into these disjoint cycles. We know, we talked about it last week, that the permutation pi has order given by the least common multiple of 9 and 4, which is 36, 9, 4, and 1. Its order is 36 as an element of S14. That means the 36th power of pi is the first one to be equal to the identity element, and that the cyclic subgroup of S14 generated by pi has order 36. Okay, what are we saying there? We're saying that if we continue applying pi, so if we apply pi twice, then we're taking 1 to 3, 3 to 14, 14 to 2, and so on. We're taking 7 to 13. If you apply pi 9 times, then that permutation will take each element in the 9th cycle back to itself, but it wouldn't do the same for the 4th cycle. If you apply pi 4 times, that permutation would take each element in the 4th cycle back to itself, but it wouldn't do that job for the 9th cycle. So if you want to ask yourself what's the least power of pi that's equal to the identity that takes everything back to itself, the answer is, well, that power must be a multiple of 9, and it must be a multiple of 4 in order that that power of pi would fix all the elements in the 9th cycle and all the elements that are moved by the 4th cycle. So 36 is the order of pi, and pi within S14 generates a cyclic subgroup of order 36. Okay, that subgroup has 36 elements in it. They're all the distinct elements that you can get by repeatedly composing the permutation pi with itself. The 36th one is the identity element. The rest of them are different permutations. Okay, so we're going to call that subgroup G. So G, what is it? It's a subgroup of S14. S14 obviously is a huge group. It's got order 14 factorial, which is an enormous number. G is a subgroup of S14 consisting only of those elements that are powers of this particular pi, and it's a relatively small group. It's got 36 elements. Okay, so we have mentioned before that the sets consisting of the element 5, which is a fixed point of pi, the elements 7, 10, 12, and 13, which are the ones moved by the 4 cycle in pi, and the set consisting of the 9 elements that are moved by the 9 cycle. We've referred to them previously as orbits of the permutation pi itself. Okay, which is absolutely fine. That's a completely standard thing to do when you're talking about a permutation. There's another context in which we also interpret this word orbit, which is closely related, but not quite the same. So from the viewpoint of group actions, we say that the group G, which is the cyclic subgroup of S14 generated by pi, that's a group of order 36, we say that G acts on the set 1 through 14. Okay? That means that every element of G determines a permutation of the elements 1 through 14. Okay, that's not anything new. We're interpreting G as a group of permutations of those elements. So we're not saying anything new there. But in that context, we would say that the sets consisting of the fixed point 5, 7, 10, 12, 13, and 1, 2, 3, 4, 6, 8, 9, 11, 14, the respective sets that appear within the 3 cycles in the disjoint cycle description of pi, we would say that those are the orbits of the action of the group G on the set 1 through 14. Okay. What that means is that when we look at the elements of that group, which are the powers of pi, if we take a pair of elements in our set 1 through 14, so for example, take 2 and 7 or something like that, that there's an element of the cyclic group generated by pi that takes 2 to 7 if and only if 2 and 7 are in the same orbit. Okay, they're not. They're in different orbits. Okay. So that means that there's no power of pi that takes 2 to 7. Okay, and we can believe that when we look at the disjoint cycle description. Every power of pi is going to take either 12, 13, or 10, or 7 to 7. Okay, there's no power of pi that will mix up the elements that are permuted by the 9 cycle and the elements that are permuted by the 4 cycle. Okay, so if we say that 2 elements are in the same orbit for a group action, it means that there's some element in the group that takes the first of them to the second as a permutation. Okay. If we take 2 elements of the same orbit, for example, 3 and 9 here, that should mean that there's some power of pi, some element in the cyclic subgroup generated by pi, that as a permutation takes 3 to 9. And if we look at that, well, pi takes 3 to 8, pi squared takes 3 to 14, pi cubed takes 3 to 4, pi to the 4th takes 3 to 2, and pi to the 5th does take 3 to 9. If we apply pi 5 times, we've applied it 5 times, we go 1, 2, 3, 4, 5. We've taken 3 to 9. Okay. 3 and 9 are in the same orbit under the action of G on the set 1 through 14. That means that there's some element in the cyclic subgroup generated by pi, the group G, that defines a permutation that takes 3 to 9. Okay. 3 and 10 are in different orbits for that permutation, for that action. That means that there's no element of the cyclic subgroup generated by pi that takes 3 to 10. No matter how many times we apply pi, we're not going to mix up the elements of this orbit with the elements in that one. Okay, so the orbits are sort of separated by the group action. Okay, we're going to have lots more examples and we're going to have a more formal definition as well. So if you can kind of get a sense of what an orbit is from this discussion, that's really all that we're aiming for at the moment. So, don't worry if you can't sort of quote exactly what the definition is. We'll have a look at that in the next video. So, other remark, if we take the full symmetric group S14, so there are 2 groups here. The S14 is the full symmetric group of all permutations of 1 through 14. Within that, we have the subgroup, which we're calling G, consisting only of the powers of that particular element pi. So the full symmetric group S14 also acts on the set 1, 2, up to 14. Okay, that's all permutations. It's a huge group. It's got order 14 factorial. And if you want to think about what are the orbits for that action, well, no matter what two elements you take here, of 1 through 14, or even take the same element twice, if you take, 2 and 11, let's say, certainly there are permutations in S14 that take 2 to 11, plenty of them. Okay, there are permutations in S14 that take 2 to 2. There are plenty of permutations in S14 that take any one of these 14 elements to any other specific one. So we would say there's only one orbit for the action of S14 on the set 1, 2, 3 up to 14. That single orbit includes all elements of the set. What that means is that given any pair of elements drawn from 1 to 14, a pair of distinct elements or the same element twice, doesn't matter, that there are permutations in S14 that take your first element to the second one. Okay, that S14, the action of S14 on this set of 14 things mixes them all up fully. There are elements there that take any particular thing here to any particular thing here. Contrast that with the case of this subgroup G. There's no element of G that takes 3 to 10, but there certainly are elements in S14 that take 3 to 10. So for the action of the full symmetric group S14 on set 1 through 14, there's only one orbit. For the action of its small subgroup G, the cyclic subgroup generated by pi, there are 3 orbits. One consists of only the element 5, one consists of the 4 elements 7, 10, 12, 13, and the other one consists of the remaining 9 elements. Okay, so whenever you've got a group acting as permutations of some set, you have this concept that the set falls into orbits under the group. There might only be one orbit. In that case, the action is referred to as transitive, but there might be more than one. And in that case, we can be interested in what they look like and what we can do with them. So one final example in this first introduction. If you take dihedral groups, so D6 is in this picture, but you can take any dihedral group that you like, acting as a group of symmetries of a regular polygon. Okay, so D6, for example, is the group of symmetries of the equilateral triangle. The equilateral triangle, I suppose, it's not exactly a set, it's a geometric object. But if we look at the set of its 3 vertices, A, B, and C, that sort of corresponds to the triangle, at least in terms of how we might describe symmetries. So the assertion here is that the group D6, it's the group of symmetries of the equilateral triangle. It has 6 elements, it has 3 rotations and 3 reflections. Each symmetry might be regarded as a permutation of the 3 vertices A, B, and C, or at least as sort of inducing a permutation of the 3 vertices. So if we interpret elements of D6 as giving us permutations of the vertex set ABC, we could say that D6 acts on the set ABC of vertices of the triangle. Okay, every element of D6 corresponds to a permutation of those 3 vertices. That's what we really mean by saying that D6 acts on that set. A bit of notation here, which is quite standard in the language of group actions. If you want to ask yourself, well, what does the rotation through 120? That's an element of D6. What does it do to the vertex A, which is an element of the set that's being acted on? Okay, we would denote the result of that by rotation through 120, and this is a dot, which is kind of at the level of the center of the line here. It's not at the lower level. So we'd say that rotation 120, if we hit A with that, we can represent that by this notation, and we would say that the result of that is C. So this is sort of saying we've got an action of D6 on the set ABC of vertices of the triangle. And here it's important to kind of keep track of what everything is. R120 is an element of the group that's acting. A is an element of the set of things that's being acted on. Okay, so A, B, C, they're just vertices of this triangle. And in particular, the set ABC doesn't have algebraic structure of its own. It's a set of things being acted on. So we're not exactly saying that we can multiply A by the rotation through 120, which this notation might kind of suggest. But we're saying that under the action, we can hit the vertex A with any element of our group, for example, the rotation through 120. The result of that is the vertex C. That's just saying that the rotation through 120 rotates 120 degrees in a counterclockwise direction, so it takes A to the home of C. Okay, so hit A with the rotation through 120, you get C. That's what this shorthand notation is saying. Hit A with TL, which is the reflection in the line L. That line passes through A, so when you hit A with TL, you just get A. Hit C with TM, here's C. TM is the reflection in the line M, which is that one that passes through B. So you hit C with TM and you reflect in M, you get A. So C hit with TM gives us A. That's what this notation is sort of valuable for as a shorthand for describing that position. Okay. So we're saying here A, B, and C are being permuted by the elements of this group. So we can take any one of those elements hit it with our favorite element of the group, and we get another element of our set. Okay. So in this case, there's a single orbit consisting of all three vertices. That's just saying that if we take any vertex and any other one, or the same one again, there are elements in the group that will take any vertex to any vertex. We can get from B to A by taking the reflection in N or the rotation through 120 and so on. So there's only one orbit. The set is not split into different parts by the action of this group. Given any element of the set, by applying different group elements, we can get to any other one. That's what it means to say that it's a single orbit. Another remark, the elements of D6 that send the vertex A to itself are the identity element. No other rotation does it, but there's one reflection that does it, namely the reflection in L. Okay, so the elements of D6 that, for example, send the vertex A to itself are the identity element and the reflection TL. So another bit of language, we say that the stabilizer of A consists of the identity element and the reflection in L. Those are the two elements of the group that fix or stabilize the element A of the set. Okay, and we can observe that the subset of the group consisting of the identity and TL is a subgroup of D6, not just a subset. And we can also observe that that subgroup has two elements. If we look at the orbit of A, that means the set of all vertices that you can get to by applying symmetries of the triangle to A. You can stay where you are by applying TL or the identity. You can get to C by applying TM or the rotation through 120. You can get to B by applying Tn or the rotation through 240. So the orbit that A belongs to has three elements in it, A, B, and C. The stabilizer of A has two elements, identity and TL. And if we multiply 2 by 3, we get the group order, which is not a coincidence. Okay, so just bear that in mind as an example, and we will come back shortly, probably not in the next video, but in the first one of next week, to discuss this connection between the number of elements in the orbit, in an orbit under a group action, and the order of stabilizers. Okay, that's it for this one. If you take nothing else away from it, just try to kind of get used to the idea of a group acting as a set of permutations and of these terms, orbit and stabilizer. We don't have a challenge connected to this video. We'll have one in the next one. So that's it for this one. Thank you very much, everybody, and we'll see you soon.